I think I'm ready to start. I'm a static analysis developer. I work mostly on Smatch. Static analysis, probably most of you know, it's when you look at the code and you find the bugs before running it, without running it, just from looking at the code. The Linux kernel, when I started, did not use a lot of static analysis. Back in 2009, kernel was there, sparse was there, but these days we use, it was more of an ad hoc thing, but these days we use a lot of static analysis, and about 2 to 4% of patches come from static analysis, I would say. And then I looked at stable kernels, and about 2 to 4% as well are also static analysis fixes, which to me is surprising because you would think they would get, all the bugs would get fixed immediately before it hits stable. But what happens is the static analysis tools are always getting better, and also people are adopting static analysis where they haven't before, such as maybe ARM, or recently I was running Smatch on ARM32, and that hadn't happened in the past. So we're finding old bugs. The more we adopt it and the more we develop our static analysis tools, we find old bugs and backport the fixes back to stable. So to me, it's surprising that it's a measure of how we're improving over time as well. So of course, static analysis, it saves developer time. People complain sometimes. Most people are very nice, but out of 99 really nice people, and you get one person complaining, and you remember that. But actually, static analysis saves time, and it prevents issues for customers, and it's fantastic. So the tools that we use in the Linux kernel, if you compile the kernel with w equals 1, it'll give you a lot of warnings. Most of them are not great. Check patch, of course, gives you a lot of warnings. Coverity, people are doing coverity, especially Colin King stands out, but Case does a lot of coverity as well. CPP check, I have not been so impressed with it, and then recently actually there was a lot of CPP checks about unused struct members. So actually we're getting quite a few CPP checks in recent months. Sparse is a tool that Linus Torvalds developed, and kernel is the most popular in terms of patches in the kernel. kernel, Julia Leroy wrote it, and what it does is it writes patches for you. And so it can also detect bugs, but more than that, people auto-generate patches. And so it's used in hardening. So we went through all the allocations, and we changed it to use struct size, or to change it to use k-malloc array. And it generates hundreds of patches. And there's a high confidence that those patches are correct, because it doesn't make typos. It does the same thing every time. It's programmatic. And so that's why the more patches are generated with kernel than anything else. And then Smatch, that's my tool, probably second most popular in terms of kernel bugs find. So sparse, what it's really good for is if you tag data as endian data. So you can tag a struct member as endian data, or you can tag a function as accepting only big endian data, or accepting user pointers, or IOMEM pointers. And those kind of data have to be treated separately. They look like a normal pointer, but they're not. And if you treat it like a pointer, you're going to be in trouble. It's a security problem. So sparse is very good for annotating data and then flagging all the places where it's misused. And it has very few false positives because those are, it's annotated by people, and those rules are very strict and clear. When it has some false positives for other things, perhaps locking. Smatch uses sparse as a front end, so I love sparse. Coccinelle. The beauty about Coccinelle is, hands up who's written a Coccinelle script or who knows what it is. Hands up who knows what it is. Okay, most of you know what it is. The beauty of it is you can write like a very short check, like a 5-line check, and it's also very fast, and it generates the patches for you. And it runs on the code before it's been pre-processed. So for macros, Coccinelle is better than Smatch. Smatch, you can do macro checking, but it's so hard. So Smatch is my tool. It has better flow analysis than pretty much anybody, I'm going to say, that I know about. It has cross-function analysis, which is unique in open source. And it works on pre-processed code. So that could be a good thing or a bad thing, depending on. So flow analysis, it's like the math. It's like a math. Code, if you think about it, in a way, it's like a state engine. So you come into a function with a certain state. Variables are defined or undefined. And it's just math to know what a variable could be. So in this case, I've written some example codes. If x is 1, then y is 2, and otherwise it's 3. So as a human being, we can say, oh, if x is 2, then we know that y has to be 3. And Smatch does that for you in the background. It operates a state engine. And that's unique in open source software. So some of the things, so Smatch is tracking all the states at one time. So some of the things that it's tracking, it's like x could be in this variable range. It could be x is controlled by the user and set to be in a 10 to 20 range. Or variable comparisons, x is less than y. Buffer sizes. We're always dealing with levels of knowledge and confidence. So sometimes you know that x is less than 40, but other times you know that it's been range checked against an unknown value from somewhere else in the kernel. And that's good information, but so it just knows that x is capped. If we're on an impossible path, there's actually a lot of impossible to run code in the kernel, where we do a sanity check and return e-inval, but that code is never run. Like nobody ever passes invalid data to that function. And that, if you don't track that, you're going to get in trouble with, because you're going to get very confused. As part of the function, cross-function database, then we track things like, oh, if you pass it to a -100, then it's going to return e-inval. Or we track that this function returns error codes. So it tracks a number of other things as well. These are just sample things that we track. But all of them are tracked at the same time, and they're all like useful for assessing confidence levels about different things. So the cross-function analysis, this slide, it's seeding the database in a way. So it's got this function name, request region, and it's an allocation function. Then it allocates parameter number 1, and it allocates it when it returns a valid pointer. So this code, what it's used for is warning about leaks. So if it returns a null pointer, then we don't need to worry about leaks. But if it returns a valid pointer, then there's two ways it could be freed. And if we free it, fine. But if we don't free it, we're going to warn about leaks. But then this seeds the database. You have to write some other code as well. But it's data that's like this in the database. And so there's a lot of stuff in the database. And there's a function, there's a program called smdb.py. And you can look up the function, which will tell you how it's called, where it's called from, what we're passing to that function. And the smdb.py function is so extremely useful for reviewing code. Or like if you're not familiar with code, this code is so nice, by the way. Just to learn about code and see. So you can call, I don't have it there. These are just samples of the stuff it can do, but you can see which other functions implement a certain function pointer, and then you can look at them and see, oh, do they return 0 or do they return enval? And the cross-function database takes a very long time to build, but other than that, like 6 hours. But other than that, it's not hard to do. It's just one command, and everybody should do it. It's lovely, unless you're like super familiar with your code already. If you're working on new code, it's a fantastic tool. So it returns. It tracks what functions return, where struct members are set. That is, functions will tell you which functions implement a certain function pointer. The cross-function database, how it works is every time you build it, then it records all the function calls and what you're passing. So if functions call this function, then that calls this function, then that calls this function, and so on. That's like a function tree. Every time you rebuild the database, then it adds another branch to the tree. So I rebuild my cross-function database every day. And sometimes I'm loading in, like the old branches get old data. But it's like I'm used to that, and it's not normally a problem. So my function trees are quite long. After about 7 rebuilds, then it kind of stabilizes, I would say. But even just building it once, so useful. So I was saying that you track user data. And user data, you get it from somewhere, and then you pass it down. So that cross-function database, super useful. There's some difficult problems. Recursion is impossible. And although I say it's impossible, but like there's many cases where you can solve the halting problem. Sometimes you can't. That's why it's called the halting problem. But other times you can see the recursion. So Smatch, it's tracking how every variable relates to every other variable. And that works normally within a function. But once you go outside of a function, it becomes too much data. So what happens is when you call a function, it squishes it down to one record. The other problem is Smatch is a bit slow. Smatch takes a shortcut parsing loops, so it parses like canonical for loops, but other loops, it might get confused and print false positives. It doesn't understand threads. That's something I'd like to work on. it's not like a fundamental, like, it's just math. Flow analysis is just math. But I don't have the right mental picture to solve that problem. And it's bad at tracking data in arrays. So you'd like to say that all the data in this array has been verified to be between 1 and 10. But Smatch doesn't always do that correctly. Of course, there's some unsolvable problems in static analysis. A bug versus a feature. We always debate that, and static analysis isn't going to help you. If the static analysis can't tell you about the spec or the firmware issues or the hardware issues, those things are unsolvable. But there's many, many solvable issues. So when people talk about false positives, they always complain about, when people talk about static analysis, they always complain about false positives. And I've got a few things to say. Once you fix the bugs, then everything's false positives. So in the kernel, if you look at old Smatch warnings, it's all false positives. You should only review the new warnings, and you shouldn't silence false positives. Just leave them. This is an example of a false positive, is when the code works as intended. So the temptation is to complain about unsigned is, like, what is this? It's an unsigned int. It can't be less than 0. That's not clear what was intended. But this is clear, and it does work as intended. So you shouldn't complain about the second one. You should only complain about the first one. And this is a similar thing where you've got an int I. There's a static analysis which will complain about this, saying, no, array size is unsigned. But no, that array size is small, and the for loop is going to work fine, and you should not print a warning. So I'm going to talk about 3 common problems. One problem is equals versus equals equals, assignment versus comparison. And this is like 100% solved. People used to try to write Yoda code, where you'd put things backwards. So you say if null equals equals x, and if you put an equals sign, then it would fail to compile. And that is a bad idea. The right way to solve it is through testing. Testing always has to be a part of your process. And then GCC added, when you have an assignment, a deliberate assignment, intentional assignment, then you have to have 2 parentheses. And I wrote that wrong. There's a mismatch. There should be a 3rd parentheses here. But anyways, that solved almost all the problems. Boom. Just by marking it as intentional. And here's another example of intentional stuff that's not clear. Is the ret supposed to be 0 when we hit the goto? It's not clear. But if you write it like this, it is clear. So it's better to write intentional code. Here's another example. Is it supposed to return 0? Then just write a 0 there. Then it's like intentional. So that was like a bonus rant. Okay, GCC added that, basically solved the problem. But then in check patch, we solved it a 3rd and 4th time. No, a 2nd and 3rd time, which is that we said instead of having the assignment here, we need to have it here and then check for if not x. So check patch took a solved problem and solved it again. And then Smatch came along and solved it a 3rd time and a 4th time. Because we said, if we've got a x equals constant, like that, forget about it. That's not the right thing. Or if it's an address, no, don't do that. And all those are bugs which have affected people, by the way. So since then, I looked at the code since 2007. There've been 2005, there've been 27 bugs fixed. and most of them were caught by static analysis. Some of them were caught by checkpatch, Smatch, and other static checker tools. While I was writing this talk, I had a bunch of ideas for further solutions and further things which could generate a warning. Like here, you're doing equals, assignment equals. That's a clue. You should be doing equals equals here. If you've got an assert statement, should be equals equals. Maybe we should put double parentheses around ternary, or in when we're passing it to a function. Or I saw one bug where it got it the other way, where it put equals equals when it was equals intended. So as I was writing this test, just by looking at it, I found 5 different ideas for static analysis. Meanwhile, there's very few bugs, so I'm not going to go implement them because it's not a priority. But there was a famous bug in 2009 when I started static analysis called the tun.c bug. And what happened was there was a null dereference followed by this nonsense null check, and then followed by some more code. And GCC said, no, this null check is nonsense. We've already dereferenced it. It removed it. So we added a thing saying don't remove null checks, even if they're nonsense. We added a thing which said you can't remap null. And we added static checker warnings to say, if you dereference something, don't check it for null. So that was a big bug. And when we focused on it, we found 3 different solutions for that bug. In 2014, we had another famous security bug. Now, these days, GCC will not compile code like this, or at least in the kernel, this code will not compile, because it says you need to have curly braces here and curly braces here, just based on the indenting. Because there's a copy and paste bug here. But Smatch has 2 more warnings to say that this code is unreachable. Why are we having unreachable code? And this line is indented more than this line. So that code will generate 3 warnings. And there's a related check in Smatch to do with missing error codes. I also looked at lines which have the same code on lines one after another, but that didn't work. So sometimes experiments don't work. So the typical Smatch check, you look for allocations, you look for freeze, you look at the return statement, you say, is this an error path? Do we still have anything in allocated state? And then you warn. And you write those checks as quickly, as broadly as possible, because you don't know what you're going to find, and then you filter out the false positives. So what I do is I review CVEs. Most of them these days are race conditions. And I feel like that might be because of static analysis. Because every time you fix bugs, you're like, this is the most important bug. Then there's the next most important bug, it turns out. So the other thing that I do is like, actually the user can set this to user data. And I'm like, why didn't Smatch find that? And so I add that as a new user data. But often it's just random stuff. So like in this code, we returned the wrong error code. We returned -e in val instead of false. And -e in val counts as true, which is not OK for access OK. Some new stuff that we've added, like size add and size mul. Do you know about those? Anyways, what they are is like they're very safe ways of adding and multiplying. We should add checks for if you take that result and use it in math, or you take that result and you store it in an int, or you pass it to something that takes an int. They've added some new scope-based cleanup in the kernel. If you don't assign it right away, that can be a source of bugs. Or these are ideas that I've never seen, but I added checks for them just because I'm sure that soon I will. What happens is you allocate this dev, And then when it hits the end of the scope, if you haven't set that to null, it will free it. So you set it to null in the success path. But if you add it to like a list, then you've got a freed pointer on the list. So maybe we could make a rule that's saying, no, don't add it to the list, because otherwise you're going to have to remove it from the list before the end of the scope. So I was recently reviewing fixes for a talk, and I noticed a bug which had to do with there was no I++ in the function. There was a variable declared as int I, and there was no I++. So I wrote a check for that, and it found like 7 bugs. So like nobody's gonna, it's a silly rule that every I has to have a ++, but it works. Turns out that I is not always used for indexes or for loops, but most of the false positives I was able to silence one way or the other. Here's another bug. The bug here is that it should have been equals equals instead of a minus. And what clued me into this was that private is 1 and this is 2. So this gives you a range list of 0 to -1, and that's a silly number. Nothing ever, and nothing good comes in 10 to -1. It should be 10 to 0 or 9 to 0. It should always end on 0. So that, like, just by that one suspicious rule, you're able to fix it. So what I'm saying is, once a month, look at your fixes, or periodically look at your fixes and think about, is there any kind of clue how I could use to mark this as suspicious? You don't have to fix the whole world. You can just nibble away at it. And even if it's something like I++ that seems suspicious, but it works, then it's results that count. So that's Smatch or static analysis. Use any tool, right? Use checkpatch. I've written a lot of checkpatch code. I've written probably a handful of checkpatch fixes to add features to checkpatch. But checkpatch, people run it every time, so it's quicker than Smatch, and you should add your stuff to every tool. So that's my email address, and that's the Smatch mailing address. Are there any questions? Yeah.
In the first example you gave about not fixing false positives,
Yeah.
I think it was about checking less than 0 in an unsigned variable.
Yeah.
And you said just complain about the first case, not the second.
Yes.
So you think it's not worth it removing the x less than 0 condition in the second if?
This is a GCC warning, and Linus Torvalds doesn't like this. He doesn't like that GCC warns about this. So for a long time, the Linux kernel didn't have that, and now it does on almost everywhere. So of course you have to fix it. And you can't really fight against GCC on that. But I would say it shouldn't have been a warning. Yeah, but you have to fix it because it's GCC warning. Can't leave GCC warnings.
But why is it bad to remove? Like, why is it not a good idea to remove the x less than 0 check?
No, I mean, it's a GCC warning. You have to fix it. This code is very readable. So you know, on the next line, you know, you got 0 to 9, right? If you remove it, you're slightly hurting readability, I would say. Otherwise you have to look at, it's less than 9, and then you have to look up here and say, okay. So at the same time, most people would read it. So it's not really an issue. But I would say they should go through and remove false positives. It's a step in writing static checker warnings. So your assumption is, why would anybody check that x is less than 0, right? And then you're like, oh, this is harmless. So your assumptions are always going to be changed by real life, yeah. And sometimes, like here, Smatch will know that x is an error pointer, not an error pointer, an error code. So Smatch can warn about that. So you look at can I use some other clues to make that code better, that check better? Yeah.
Are you following a particular coding standard there, or are you in a position of being opinionated and effectively you're defining your own coding standard here? And what do you have to
I'm an expert on Linux kernel style. I would say, yeah. I know almost everybody's opinion on Linux kernel style because I deal with every subsystem. So not everybody agrees with me. Yeah.
Would you go beyond the Linux
I would
kernel
not.
style?
No, the point is, when I'm writing code, I'm tempted. I'm like very tempted to say, oh, you should be writing this in a much better way. No, this code works, and I don't necessarily agree with it, or whatever. If the code works, leave it. I'm not going to complain to you. I'm not in a. I have a lot of opinions about style, but I'm not. I'm avoiding that. Yeah.
Thanks.
So like check patch, can it run out of tree, this tool?
I believe it can. I know that other projects use it, like U-boot.
Okay, yep. Thank you.
Yeah.
You said you should only look at the new warnings. Is there some tooling to keep track of the new warnings, or
Wow,
do you have to?
that is a great question. I do have a tool which is so garbage, but yeah, under Smatch scripts, there's a new warnings thing, and it saves it under. Anyways, it is a very garbage tool, but that's what I use, and it works quite well. Yeah. Any other questions? I don't know how we're doing on time. Yeah, did you have a question? Okay. All right, I think we're okay on time. So thank you very much. Let me, this is the email address, and if you have ideas about checks that you want, just send it to me or to the mailing list, and always put like a specific bug, like so we can look at specific code when you're talking about bugs. So, all right, thank you.